Let's start. Our first speaker for today is Zihong Chen, and he's going to tell us about Kontsevich-Soibelman operations from the periodic system.
Yeah, thanks for the introduction, and I want to thank the organizers for this wonderful conference, and thank you all for coming on the last day. So that's the topic of my talk. It will be roughly in two parts. So part one, I'll talk about mainly just some operads, their equivariant homology, and how they sort of act on, the Hochschild variance of a DG algebra. And in part two, I want to talk about some applications to non-commutative Hodge theory and symplectic topology. So for this part, I will sort of consciously look back to things that Simon and Jay has talked about in their talks and sort of provide a new perspective on some of the things. So, okay, let's start with the setup. So A is DG category or DG algebra over or base ring R. It can be Z or Z mod 2 graded. Then we have its Hochschild invariance. This was introduced in Simon's talk where he's mentioned the spectral version of this, but today I'm just going to focus on the good old linear algebra version. So the Hochschild cochains are just this big direct product of multilinear maps. It has an internal differential, which is given by the differential on A itself, and external differential, which is given by this formula. I hope everybody's already pretty familiar with this. And dually, we have the Hochschild chains, which is this big direct sum of shifted copy of tensor products. And we think of this as the cyclic bar construction, and draw the entries of A on the circle. And here, differentials are just given by multiplying the adjacent elements. So we're interested in sort of algebraic operations on this pair, consisting of the Hochschild chain and cochains. And one of the most important, statement about this is known as Deligne's conjecture, which is now a theorem. So it says there is an action of the operad of the chains on little disk operad on the Hochschild cochains of any DG algebra A. So this was proved around 2000s by a bunch of groups, including Kontsevich-Soibelman, Smith, Tamarkin, Marinov. So first note, this is a chain level action, but it has some consequences for what actions there are on the cohomology. So namely, we should expect a lot of operations on Hochschild homology coming from the homology or the equivariant homology of the little disk operad. So here the sigma n denotes the symmetric group action that permutes the labels of the disks. So for example, we have this degree 0 homology class. So that is just the coproduct. And there's a degree 1 homology class given by rotating the second disk around the first disk. And that gives rise to the Lie bracket on Hochschild homology. So if you work over the rational numbers, that's the end of story, because it is known that these two operations generate the homology operad of little disks. And over Q, it is known that little disk operad is formal, namely it's quasi-isomorphic to its homology operad, also known as the Gersten-Haber operad. But the story becomes more interesting if you work over a field of characteristic P. And there, the E2 opera is non-formal. And the non-formality is exactly can be seen from these interesting equivariant homology classes, the sigma P equivariant homology class. And these are fully computed by the work of Cohen. So those generalized in degree P-1 and P-2, they give rise to operations that are now called the Dyer-Lashev-Cohen operations. Hochschild homology, let me just give an example of this degree P-1 generator. Okay, so this gives rise to this operation. There's a slight catch with this degree here, has to do with the sign representation, but let me just sweep it under the rug. So in general, I don't know how to draw this P-1 cycle, but for P equals 2, it's just one cycle and it's easy to draw. Okay, so it is this half twist given by sort of permuting just twisting the two disks, exchanging their positions. This is a well-defined cycle in equivariant homology. And explicitly, it gives rise to the so-called brace operation, or sometimes also called the circle operation, Hochschild cochain. So it's half the Lie bracket, if you can think in this way. So the thing I'm interested in is how to generalize this picture to include the Hochschild chains, not just the Hochschild cochains, right? And this was done in the work of Kontsevich-Soibelman. So they generalized the little disk operad to a two-colored DG operad, which comes from the chains of a topological operad. Okay, so roughly speaking, this operad, which we call KS, has two sequences of chain complexes. So the first sequence, so here, let me just explain. So 0 and 1 denotes the two colors. And NM are the two indices in the two sequences. So the first sequence is just the chains on the disk operad. The second sequence is chains on the space of configurations of M disk on a cylinder, plus the data of two marked points on the boundary. And we consider these over modular overall rotation. So I draw a picture on the left. Okay, so to prescribe the operatic structure, I have to tell you, there are three types of operatic structure. The first type only concerns the first sequence of spaces, which is just the operatic structure of little disks. And the second type, which is very similar to the first type, it involves one element of the first sequence and one element of the second sequence, and it's given by just inserting a configuration of disk in a disk, into some disk on a cylinder. I hope this picture is self-explanatory. And there's a final type of composition, which only involves elements of the second sequence, and it's given by stacking two cylinders on top of each other in a way that matches the input of the second one with the output of the first one. Okay. So the key thing about this opera is that it acts on the pair given by the Hochschild cochains and Hochschild chains. So this was proved by Kontsevich-Soibelman, and it generalized this Deligne's conjecture. So in particular, there's a chain map from this KSN1 to homomorphism, the homomorphism complex from n tensor copies of Hochschild cochains, one copy of Hochschild chain to one copy of Hochschild chain. So the way to visualize this is if you're given such a cylinder, each of the n disks should correspond to the input of Hochschild cochain. The upper boundary corresponds to the input Hochschild chain, and the output lies at the lower boundary, which is a copy of Hochschild chain. So example, so this 0 cycle here gives the cap product or the contraction action of Hochschild cochains on Hochschild chains, and this degree 1 homology class is a Lie action. So for instance, if you want to prove the Catan formula in this case, here's the pictorial proof. Well, you just show that the stacking of the contraction with the con operator, which represented by the circle action, and con operator composed with this contraction is homologous to this one cycle that represents the Lie action. Okay, so that's an example. But we're interested in some more interesting operations, just like the previous dielectric coherent operations. They come from equivariant homology, potentially characteriscopy. Okay, so that is the main question for this talk. So let me first try to formulate this question more precisely. So I want to note that this chain map, which I call star, is not just a chain map, it has some equivariance. Okay, so on this group, there's an action by sigma n cross S1 cross S1. So the symmetric group acts by permuting the labels of the disks. The two circles acts by rotating the two marked points on the boundary. But on the right-hand side, there's also similar actions. So there's a symmetric group acting by permuting the factors of Hochschild cochains. And there's two S1 actions given by the usual circle action on Hochschild chain. And this star is supposed to be equivariant with respect to this action. So what I mean by studying the equivariant operations is by taking suitable homotopy fixed point and homotopy orbits, we can get a map like this. Okay, so here the S1 action is the diagonal circle sitting inside the two copies. So what this tells us, if you fix a homology class of this guy, if you fix a homology class of this guy, then you get an endomorphism of the homology of this guy, which is also known as a periodic, or in this case, negative cyclic homology. But I only want to consider the induced action on the periodic cyclic homology. Okay, and definition, an element or endomorphism of the periodic cyclic homology arising this way is called a KS Kontsevich-Soibelman operation. Okay, so our first goal is to describe all these operations. So guys, by describe, I really mean, there are two aspects. Maybe first, we want to classify some kind of abstract generators in the equivariant homology of this operad. And then we want to give a explicit interpretation of these generators. So here's the main theorem. It's actually pretty simple. So first, if the answer depends very much on your coefficient field, or coefficient ring in this case. So if the ring contains the rationals, then there are no non-trivial KS operations. So this statement is one of the reasons I'm using periodic homology, because if you use the negative version, this statement is not true. On the other hand, if your ring contains the finite field Fp, then there are some non-trivial ones, but all of them are generated on the composition by one single type of operation. Okay, so this is pi Cp. It's called the p-fold equivariant cap product. It was discussed in Simone's talk on the first day. Okay. So the proof of this statement, yeah, please. Yeah. Sorry. So so there's an S1 action on this Hochschild chain. So HS1 is like taking the homotopy fixed point, which corresponds explicitly to negative cyclic homology. And TS1 is like the Tate fixed point, and it is the periodic cyclic homology. So here I'm inverting the variable, equivariant variable. Okay. So is there a question? Okay.
Do you know how this fits with your theorem?
That's a great question. So the quantum-Adam relation, yeah, I'm not exactly sure how it fits in this Operadic framework. I haven't really thought about it, but we can discuss afterwards. Yeah. Yes. Mm-hmm. Yeah, I think it's very likely, but I haven't really thought about it. That's my answer. Okay, so let me just briefly discuss the proof of the theorem. So there's one component which is just trying to compute the equivariant homology of this operad, and that part is very sort of visual. There's a more technical part which I won't talk about in this talk, which is why do these generators actually give rise to this explicit operation called the p-fold equivariant cap product? So that's the more technical part, but I think for this talk I will just omit it. So the first part of the proof just uses coherence computation of the equivariant homology of configuration spaces. So for instance, the statement 1 just follows from the following very simple fact. So you consider previously we were considering the simultaneous S1 action rotating the two marked points on the boundary. But of course, that's after rotation the same as rotating the lateral surface of the cylinder. And it is easy to see that the only isotropy group of this action is the finite cyclic groups. So if you work rationally, of course, they have no Tate fixed points. Okay, so that's the reason why we're using Tate instead of homotopy fixed points. And two, if your ring contains Fp, for some reason, it's easier to replace the S1 action by the finite cyclic group action. So now let's first study this gadget here. Okay, so by localization, it suffices to look at the actual CP fixed point of the quotient of the Kontsevich-Soibelman operad by the symmetric group, or in other words, the unlabeled version of this operad. So here's the picture, the result of the computation that you can deduce more or less from Cohen's work. Okay, so here's the picture. So let's look at the thing on the right. So this is a generator, or an element of the basis, a basis element of this homology. And what does this picture mean? So there's a bunch of horizontal levels. Okay, so at the bottom, you see these kind of sort of one cycles, which are given by p disks, sort of in this CP symmetric configuration, and you start moving these p disks simultaneously that preserve the CP symmetry, and you do like one piece of this full circle. So that is an equivariant cycle. And there might be a bunch of them on top of each other. So on the top, you have this fixed configuration of p disks, okay? Also in the CP symmetric configuration, but inside them, you can insert any homology class of the E2 operad. And it is inserted in a diagonal way into all the p disks. Okay, so that is the full description. And here on the left, I've drawn the interpretation in terms of configuration spaces. So if you look at this picture, so I mentioned before there are these compositions in the KS operad, which are given by stacking cylinders on top of each other. So imagine you just cut open these cylinders at these horizontal levels. So up to this kind of composition, you only get two types of generators, okay, which are these two. Okay, so the generator E1 is the one, at the bottom here. There might be a bunch of them. And then there's E0, which is on top. Okay, so you might worry about these, insertions of E2 operad, but these just correspond to replacing your Hochschild cochain by a new Hochschild cochain. Okay, but since we're only concerned with the endomorphism of the periodic cyclic homology, so that's fine. But even among these two generators, there's extra relation. Namely, it's obvious that this E1 is just obtained from E0 by rotating through one piece of the circle. So here's just another way of writing that down. I'll call this a CP Coton formula. So there's one important but easy consequence you can do from the computation, which is this element E0, which a priori is a CP fixed point of the operad, actually comes from the S1 fixed point. Okay, so that's important. So it turns out that this E0, this generator E0 is something we're familiar with. Okay, so it is the p-fold equivariant cap product from Simon's talk. So I prepared a slide to talk about explicit formulas, but I think I don't want to repeat what Simon said. So let me skip this slide, since the explicit formula is not going to be important in my applications as well. So there are some diagrammatic representation of the operation. But one consequence I want to say, which is a priori not obvious from the explicit formula, is the following, is that this operation, pi CP, which a priori only acts on the CP Tate fixed point, actually preserve the periodic cyclic homology as a summand. And that just follows from this important but easy observation that this homology class actually is restricted from S1. Okay, great. So any questions before I move on to applications? Okay, very good. So my first application, okay, so I guess I'll have some applications, two, and I'm calling them pseudo applications because in either case, there's either a missing argument, missing link in the argument, or there's a full argument, but I'm still missing some, good examples to illustrate it. So I think these are pretty much experimental. So the first application concerns the Gauss-Manin connection, and this part is, I think I want to sort of loop back to what Simon and Jay talked about in their talk. And the motivation for this application is, this relation between the p curvature of the Gauss-Manin connection or the quantum connection with some equivariant operations. And I want to provide a sort of new perspective from this operatic point of view. So the setting is, so now we're working in a relative setting. We have a ring over a base field R, a ring R over a base field K. So here you should think of R maybe just as a smooth affine curve, and it parameterizes a family of DG or A infinity categories. So Gassner defined this explicit connection, which is now called the Gassner-Gauss-Manin connection on the periodic cyclic homology, on this relative this periodic cyclic homology over R. But from now on, I will just omit this over R. And it should be understood that all cyclic homology are worked relatively. So explicitly, the formula is given by the following. So this nabla GGM, with respect to a vector field V, is given by T nabla V. So this term is given by the following. You just fix a semi-free resolution of your algebra A. You fix a basis, and you just differentiate with respect to that basis. And then there are two more terms. So iota is the contraction operator with respect to the Hochschild cochain given by the Carrera-Spencer class. So recall this is just the, fix a basis again, and expand your A infinity structure map mu with respect to this basis and differentiate the coefficients. Okay, this is a well-defined degree 2 cohomology class. And then we have a final term, which is this T times E. So this is an arrow term, which comes from, so recall when I said the Coton formula, So the non-commutative version only holds up to homotopy, and E is that homotopy. And the reason why this chain level definition descends to cyclic homology is exactly because of the Katon formula. So, okay, as Jay has introduced yesterday, so when you're given a connection, if your base field has characteristic P, there's an interesting variant called the P curvature, which we recall is just this formal difference between the pth power of the connection with the connection along the pth power of the vector field. It is a linear, our linear endomorphism. Well, it's in fact linear over this equivariant homology ring of the periodic cyclic homology. Okay, but a few minutes ago, I just talked about all these lots of other endomorphisms coming from the Kontsevich-Soibelman operator. So I think, well, here's a new endomorphism. So it's natural to ask, is this one of them, right? So the proposal is, okay, well, is the P curvature a KS operation? So as stated, this question, I think, this proposal is too naive to be true, but I will first put it out here and later make amendments to this statement. But more precisely, what I mean is that there exists a degree 0 homology class in this equivariant homology of the Kontsevich operator, such that when paired with the pth power of the quadratic class, okay, in the equivariant Hochschild cochains, gives you this P curvature. Okay, before I say why we care about this statement, let me just do a sanity check. Okay, so we can prove that, in fact, all of the operations coming from the KS operator commutes with the Gauss-Manin connection. Okay, so we're not crazy, because if you want something to agree with the P curvature, the P curvature certainly commutes with the Gauss-Manin connection, because it's just something that's built out of the connection itself, and you have a flat connection. Okay, so unfortunately for now, I don't know the answer to this question. Okay, but why do we care anyways? So the point of this operatic approach is that, so if we know that the P curvature were a KS operation, then in fact, by a posteriori classification of the operations we talked about previously, one can actually show that there's a unique generator in this degree. Okay, and that generator is this thing which I called E0, and that's exactly the operation, the equivariant homology class, that gave rise to this P-fold equivariant cap product. And so that means that if this were true, then the P curvature has to agree with this P-fold equivariant cap product up to a scalar, which you can easily fix to be 1. Okay, so this is a consequence. So the way I would think about this statement in terms of the operad is the following. So on the left-hand side, we have the P curvature of the Gauss-Manin connection, which really comes from the L infinity part of the theory. Okay, so what do I mean? So one can construct the structure of a DG Lie algebra on the Hochschild cochains, shifted by 1, I guess, adjoining these two variables. Let's call them Xc and dxc over Xc. Sorry, d over dxc. Okay, so there's a structure of DG Lie algebra on this gadget, and one can show that this thing acts in an L infinity way on the negative cyclic homology. Okay, so I'll just call it Cc minus, such that this thing acts by the Gauss-Manin connection. So this is the sense in which this connection arises from an L infinity part of the theory. But on the right-hand side, this operation, which is the P-fold equivariant cap product, it is an action of the algebra given by this equivariant Hochschild cochains on the cyclic homology. So really this thing is, I guess, its most important property is multiplicativity. Okay, sorry, I meant to write it down. Multiplicative. Sorry, is that a question? Okay. So I guess the way I would interpret the statement in this opera is then, so this is some kind of intricate relation between the L infinity and the A infinity part of the theory concerning the Hochschild invariants. So really the natural place to consider them is to extend to the E2 operator, because that's where these two different theories interact. And for instance, how does this help us? So here's a very easy corollary, which is also briefly touched upon in Jay's talk. So I'll be brief about the next few slides because it's largely overlapped with things that Jay and Simon had talked about. Okay, but just to refresh your memory, so assuming that this holds, we have the relation, and the P curvature equals this P for equivariant cap product, and assume that your algebra A is Calabi-Yau. I guess here I really mean smooth Calabi-Yau. So you have volume form. Then you can easily show that this P curvature is actually nilpotent, which is again a multiplicative property. Okay, how do you see this? Well, because we have interpreted this as this action, which is multiplicative, to show that this is nilpotent, it suffices to show that the element here is a nilpotent element of the ring of equivariant Hochschild cochains, which in turn is equivalent to showing that the operation or this characteristic class itself is nilpotent. Okay, but obviously the characteristic class is just this expansion, and if we assume your DG category A is non-curved, then this is a Hochschild cochain that belongs to the length bigger to one part, right? Because you started with mu1. So on the other hand, you have the volume form sigma in Hochschild homology, and so if you apply this this characteristic class enough times, you will get something 0, because eventually it will eat up all the length you have in your volume form. But by definition, volume form that implies the original. This power of characteristic class is 0 as well. Okay, so that's an instance of how we can utilize this multiplicative structure of the P curvature. Okay, so this. Okay, any questions so far? Maybe I should pause. So now let me move on to the A side picture. So I'll just work with a X omega, a closed monotone spectral manifold. And we would like to apply all the previous story of this operatic structure to the A infinity category given by the Fukaya category of X. So the key tool of translating this picture geometrically is the open-closed maps, which were introduced in Mohammed's talk. So there's various versions of this, the closed-open, open-closed, and cyclic open-closed, but they go between quantum homology, Hochschild homology, and Hochschild homology and various equivariant versions. So I guess to be precise, since we're working in the monotone setting, really the Fukaya category should be thought of as a curved category. Or alternatively, you can think of this as having one category for each eigenvalue of the quantum multiplication by the first Chern class. And these lambdas represent the disk potential that are bounded by your Lagrangians. So the relation between, I guess, the closed string theory of a symplectic manifold, Gromov-Witten theory, and this operatic theory on the Fukaya category is given by the following theorem. Okay, so the theorem is that if you work over a field of characteristic P, then the following diagram commutes. So roughly speaking, on the left-hand side, you have this action given by the P-fold equivariant cap product. On the right-hand side, you have this quantum string operation. And these are intertwined by the various versions of the open-closed and closed-open maps. Okay, so that is the statement of the theorem. So again, this Q sigma was discussed extensively in Jay's talk yesterday. So I will not repeat his definition, but let me just put this figure out there to refresh your memory. Okay, so it's some kind of equivariant count of genus 0 Gromov-Witten invariants. And in this case, the analog of this P curvature statement, it's this theorem concerning that the quantum string operation applied to the first Chern class agrees with the P curvature of the quantum connection. So there's by now various versions proved by J. Lee, Paul Seidel, and by Lee. And they have some applications concerning the formal structure of quantum connection over the complex numbers, such as the statement about the exponential type. Okay, so let's just have one word of what this statement is saying. So this is saying that if you restrict to the small quantum connection, so here I'm restricting the variable t to be 1, so that collapses the z grading to z mod 2 grading. So maybe this deserves to be called the small quantum connection. So this has the singularity of exponential type at q equals infinity. So meaning that if you change a variable, capital Q equals Q inverse, then there's a finite direct sum decomposition into a bunch of pieces corresponding to the eigenvalue of the first term class, such that in each summand, there's a very simple form. So it is equal to d over dq, and a quadratic pole term, which is just a scalar, and something remaining, which is regular singular. So you sub this as a eigen decomposition of the connection. So it's not regular singular, but it is the next best possible thing. Okay, so this is part of the, I guess, A model ANSI hot structure, which was formulated by Kontsevich and later by Galkin, Galush, So this is only a very small part of the structure, but for some year it has resisted the proof. I should also mention there's a very different, I guess, proof preceding my proof, given by Polymer Seidel, with some extra assumptions, based on a much more geometric approach using Fukaya categories and non-commutative Hodge theory. So that's pretty much what I want to talk about considering this aspect, but I just want to go back to this statement which I said, okay, namely this question. So I mentioned previously that it is too naive to expect this to hold on the nose. So what is the amendment we need to make? Okay, so here's the additional assumption we need. So basically, I am saying that in general, we should probably only expect to have this identification under the extra assumption that, okay, so the differentiation of the current Spencer class is 0. So this is saying that your family of DG category is a first order deformation. Okay, so namely that this equality that we have here, okay, only holds up to first order for general DG category over FP. So what is the intuition? So this is something actually mentioned to me by Jay. So really you should think of their in the background as having a filtration on the periodic cycle homology. So these is sometimes called the conjugate filtration. And really this statement is supposed to hold on the greater piece of the filtration. So that corresponds to this first order deformation assumption that I have here. But there are cases where it actually holds on those, as we have seen. But there has to be a good reason for that to be true. For instance, in Simon's talk on the first day, he mentioned a spectral lift of the statement, namely if your category over FP lifts to the sphere spectrum, then you expect this to hold on those, because this lifting is a good reason for this filtration to split. And of course, we've seen that there are these geometric proof in the case of A model that these two gadgets or these two quantities are identical on the nose. But there we really don't understand the picture very well. So there's still a lot of work to do to understand why in these particular geometric situations we have a splitting of this filtration that gave rise to this strict equality. So I think that's pretty much I want to say about the first application. Really it's a pseudo application because I didn't prove anything new using this operatic perspective, but rather it's like a new perspective on the results we've already seen in this conference. Are there any questions so far?
If the filtration doesn't, what do you expect the correction? Will it be like some higher order polynomials in curvature, or will it be something like higher order infinity?
That's a great question. So what will be the correction term? So I would say I don't have a good answer to that question, but so this phenomenon is already present on the B side as well. So there's a classical work by Katz on this algebraic solutions to the Picard-Fuchs equation. So there he studied this. So there the conjugate filtration has a more geometric interpretation, just the good filtration on the theorem complex. And in that scenario, you can describe the P curvature by explicit formula on the check complex. And basically, I think on the first order, so basically, the entire expression for the P curvature is a huge Horizontal polynomial consisting of the Lie algebra action and the contraction action in some vector field. And on the first order level, there's some miraculous cancellation that allows you to get this operation, which is given by the conjugation by the Cauchy operator of the contraction operator, which is more or less the left-hand side. But these extra terms, they're given by some polynomials which a priori do not have, or at least I don't know an interpretation. But there's these polynomials consisting of the Lie action and contraction operator. Okay, any other questions? So for my second pseudo application, I want to really discuss. So I guess here, for the first application, we've talked about the two perspectives from the operatic side and from the A model side. But really, so these are just just for the sake of intuition, but there's no really interaction between these happening. But for the second application, I want to speak about some actual result they could get from the relation between these two perspectives. And so this will be in the context of symplectic topology. So I guess I want to, so the topic will be torsion in the integral cohomology of a symplectic manifold, which may be a not very well studied thing in literature. So first of all, I want to recall that the quantum Stingray operation is a quantization of the classical Stingray operation. So that means that if you restrict to the contribution from the constant J homomorphic spheres, then that's just the cup product with the classical Stingrod, which is this power series in the equivariant variables t and theta. So I want to draw attention to this theta term. Okay. So namely, each theta term comes with the Bockstein operation. Okay. So the same actually also holds for the prime p equals 2. It's just here you see that the powers of t can be fractional. And the convention is that we let theta be t to the 1/2. And so the odd Stingray squares also contains a Bockstein. Okay, so in particular, if you have p torsion in the integral cohomology of your symplectic manifold, meaning there's a non-trivial Bockstein, then the classical Stingrod, in particular the quantum Stingrod, has a non-trivial theta term. Okay, so that's just a very visible fact I want to point out. So how does this matter? So I want to recall 3 statements which we've learned through this talk, which are in tension with each other. So here are the 3 statements. Okay, first, what I just said. If you have torsion in your integral cohomology, then the quantum Stingray operation has non-zero theta term. So intuitively, this is saying that there is some information from the CP equivariant theory, which is not coming from the restriction of the S1 theory. So that is what theta is about. On the other hand, we saw that this P4 equivariant cap product, which come from this equivariant class in the Kontsevich-Soibelman operad, preserve the summand given by the periodic homology in the CP equivariant homology. So recall the way we prove this is by showing the equivariant homology class that this corresponds to comes from the restriction of the S1 class. Okay, so that's another way of saying there's no theta term. And finally, recall we had this theorem that when A is the Fukaya category, there's compatibility between this P4 equivariant action with the quantum Stingrod. So in particular, if the comparison, the open-closed string maps are isomorphism, namely if Abzai's general criterion holds over your field of characteristic P, then there's literally an identification between these two things. Okay, but of course, well, 2 is just a fact. It's always true. So that means the assumptions of 1 and 3 cannot both be true, right? Because otherwise you have a contradiction. So immediately we got a corollary, which is if your integral homology has p torsion, then your manifold cannot satisfy general criterion over fp bar. Okay, so this is an obstruction to general criterion for some arithmetic reason. So I think it's natural to wonder whether this is something genuine about flow theory or Gromov-Witten theory, or it's just some stupid topological thing. But I want to point out one fact which I think points in this favor. Okay, so this is, okay, just observe that this corollary is obviously false for a non-closed symplectic manifold. Okay, so for example, take X to be the cotangent bundle of any closed-oriented manifold Q, then it's a result of psi that the cotangent fiber always generates the wrapped Fukaya category. Okay. In fact, over the integers. So that's always true, regardless of what Q is. So in particular, Q can have as many torsion as you want, but it still generates. So what's going on here? So the point being that, of course, you can also consider these categorical operatic operations on the wrapped Fukaya category of T star Q, for instance. And there's these analogs of the quantum string operations known as the equivariant pair of pants, defined by Seidel and Shilukin Zhao. But in this case, these operations recover some equivariant homology operations from string topology. And there's no hope for you to recover the sting rod, the classical sting rod, and the Bochsteins from these string topology operations. So if you look at the framework that Peter May has for how to define string operations algebraically, you see the key difference is that in the closed case, we have a trivial S1 action on quantum homology on the chain level. So somehow I think it's a miracle, even though it's taken for granted given its name, that the classical part of quantum string operation is actually the string operations. Okay. Okay, but I think this statement perhaps is a bit abstract, meaning how do you actually interpret what it's saying that over FP bar you don't have generation. So for the next, I guess, last probably 10 minutes of my talk, I will try to give a attempt at explaining this phenomenon geometrically. But I do want to warn you that the last part of this talk will be, a bit experimental, and there are some results which I'm not sure if they're non-trivial. So if you spotted a one-line proof of anything I'm going to say, you should let me know. So this geometric interpretation comes from the following angle. So this corollary is saying that if there's torsion, then there are things in the quantum homology that you cannot see from the geometry of Lagrangians. But what about those things we already knew are in the image of the open closed map? Okay, so can we say more about those? So that's the angle I want to take in this last part. So I want to find some instructions through Lagrangian realization in the following sense. So if M is any closed-oriented manifold, okay, we say a cohomology class is realized by either an embedded or immersed oriented submanifold if it is a Poincare dual to the fundamental class of this submanifold. So this is a really classical question topology trending in the 1950s to study what obstructions and what necessary conditions there must have. So this is known as, I guess, a partial case of sting rod problem, and this was largely resolved in the stable range by this famous paper of Tom, where he defined the cobordism ring. So in fact, this problem is one of his motivation to study the cobordism ring. But it's natural, if we are interested in symplectic manifolds, to ask if you have a two-n-dimensional symplectic manifold and a middle cohomology class, when can be realized by a Lagrangian submanifold? Okay. So surprisingly, I couldn't find a lot of literature on this particular topic. So there's a lot of literature on saying computing the Lagrangian cobordism ring. And there's a lot of literature on sort of Lagrangian rigidity, meaning that if you have a Lagrangian embedding into a fixed symplectic manifold, what constraints does it put on your Lagrangian L? But I couldn't find a lot of literature on this problem of when a middle homology class can be realized. So if you are aware of such literature, I'll be very happy you can let me know. Okay, but it just seems to be a natural question to consider. So here is the necessary condition, which we can deduce from these equivariant theory of, I guess, Gromov-Witten invariance. Okay, so the theorem is the following. If you have a closed monotone symplectic manifold and a FP middle homology class, so suppose this homology class can be realized by a Lagrangian that supports an object, that's Fukaya category. So here I just means, okay, so because I work in the monotone case, this means a closed monotone Lagrangian. And if your P is not 2, you should also add this relative spin condition. So if this supports Lagrangian, then here's the necessary condition that this alpha has to cup 0 with all the images, all things in the images of Bochstein. So of course, this criterion is only useful if your manifold has non-trivial torsion, but somehow there's this very simple, purely topological condition. So let me just briefly discuss the proof. It basically follows from what we learned in this talk pretty easily. Okay, so let Y be any class in the periodic homology of the Fukaya category, and B be any class in the quantum homology. So previously, we thought this theorem about the compatibility of this P4 equivariant cap product with the quantum steam rod, and here's the exact statement. So we have this. But we can just let this Y to be the unit class of any Lagrangian. Okay, so here, I guess, Fukaya category doesn't have strict units on the nose, but you can just take EL to be either homotopy unit, or since we're only considering one Lagrangian, you can just take it to be the fundamental class in the Morse homology of L, such in Sebastian's talk yesterday. Okay, so there are strict units. And then standard argument in floor theory will imply that the image under the cyclic closed map is just the Poincare dual to its fundamental class. So basically the reason is because this is the contribution from the constant homomorphic disk, and all the non-constant ones can be perturbed away to have extra symmetry. So these are all degenerate moduli spaces. So what does this tell us? Okay, so if we plug in Y equals EL here, we know the left-hand side has no theta terms, but the right-hand side potentially has if there's torsion. But in any case, we're able to conclude that at least this term, the Q sigma, applied to the homology class of L has no theta terms. And if we try to figure out what that means on the constant terms, that's just saying that the homology class of L coupled with anything in the Bochstein has to be 0. Okay, so that's how we get this conclusion. So, okay, so I think this statement is something that confuses me, and so let me just put another caution sign here. So the reason is because you have such a simple and purely topological obstruction, it is natural to wonder whether this obstruction has any floor theoretic or symplectic meaning. So what am I saying? Okay, so let me sort of zoom out a bit. So here's the question we're considering, right? So on the right-hand side, we have the singular homology of our symplectic manifold X. And on the left-hand side, we have all those different cobordism theories, which I will describe in a bit. And we're trying to study the image of this cobordism theory in this singular homology, okay, by mapping a class of manifolds into their fundamental class. And we're asking, how unsurjective are these horizontal maps? Okay, because none of them are surjective. So for instance, so the bottom two cases, okay, so loop X just denotes the cobordism ring of immersed submanifolds, and this loop embedding of X is the embedded cobordism ring. So these are studied in the work of Tom. Okay, so I'll call this case X classical or boring, not in the sense they're boring, but they're boring from the symplectic perspective. Okay. And the next two cases, which I'll call the flexible case. So this thing here is the cobordism ring of Lagrangian immersions. This thing here is the cobordism ring of Lagrangian embeddings. So there's a theorem of Gromov-Witten called the H principle. Okay, so it's Gromov-Witten H principle that says that the data of a Lagrangian immersion is homotopic to the data of an immersion together with the Lagrangian Gauss map. Okay, so it's immersion plus some purely linear algebraic data. So that means there's a Tom space that classifies such immersions, and you can study this purely in an algebraic topological way. A priori, this cobordism ring of Lagrangian embedding is more rigid, it's more complicated, but for the sake of studying their images in a singular cohomology, these two things are actually pretty much the same. So there's also a theorem of Kontsevich using Lagrangian surgery that says roughly that, at least in a lot of cases, the images of, if a homology class is realized by Lagrangian immersion, it can also be realized by Lagrangian embedding. So the basic idea is you resolve the double point of the immersion by Lagrangian surgery. And finally, we have the top case, okay, which I guess I'll call the rigid case. So this consists of, for instance, monotone cobordism of monotone Lagrangians. So it's called rigid because they are the ones that interact substantially with flow theory. So for instance, this classical theorem Chekhov says that if L1 is monotonely cobordant to L2, then they have the same mass of 2 discount. And this was generalized substantially by the work of Baron-Kania, which says that if they're cobordant monotonely, then they have the same Floer theory in all of their A infinity structures. Okay, so as I guess the concluding remarks, let me just say, we know from the above theorem that if this purely topological condition fails, okay, so we have this criterion. If this fails, my previous theorem says that this homology class alpha cannot be realized by a rigid Lagrangian. But of course, the real question is, where does the obstruction take place? Could it be possible that this condition, the failure condition, simply obstructs the realization of alpha by a submanifold? Because that would be very boring. So I don't have a full answer to this question. So I can tell you what I know about the triviality / non-triviality of this statement. So the only thing I can show is that there exists example, Fano, and middle cohomology class, such that alpha can be realized by embedded submanifold, and of course this is trivial, well not trivial, but obvious condition that it has to cup trivially with the symplectic form, otherwise it cannot be a Lagrangian in the real cohomology. So there's a middle cohomology that satisfies these two conditions, but fails this criterion. So what is the example? Yes, let me briefly mention this. Okay, so this example comes from this construction of Olson-Ranimal. It's quite recent construction. So it is the first known Fano to have torsion in H3. So the reason why they care about H3 is because this is birational invariant. So somehow you have to do something smart to construct torsion in this range. So roughly speaking, it is the following construction. So you start with the space of quadrics in Cn, and you restrict to the space of rank 4 quadrics. Okay, and there's a way to form a double cover over this Z4n bar, which is branch along the locus rank 3 quadrics. So one can show that this is a funnel with Gorenstein canonical singularities. And then you just cut it down by a bunch of generic hyperplanes that avoids the singularity, so you get a smooth funnel. Okay, so that is the funnel that we're concerned. So the intuition behind their construction is that this is an algebraic approximation to the classifying space of BGO. So BGO is a group of matrices. So GO is the matrices that preserves the standard quadratic form up to scaling. Okay, so one example is a funnel fourfold. So there's a torsion class in H3 is 2 torsion, and it is the image of Bockstein. And the example is constructed out of this X, by coupling together. Well, you take this product, but I think the specific doesn't matter. But basically, the idea is you can construct a middle homology class such that using classical theorems of Tom can prove it is realized by some manifold. But also it couples non-trivially with the Bockstein. So this gives you like one example that this criteria is not completely trivial, but I'm still worried. I guess the place why I'm worried is that, let's go back to this diagram. So we know that from this thing that this does not belong to this class. Belong here. Okay. But I do not know whether this condition obstructs a flexible Lagrangian immersion. I think, yes, it's torsion. That's right. Okay, so I guess so here I'm not considering local systems on Lagrangian because the statement about Lagrangian being the image of open closed map, somehow that statement is independent of local system because it only comes from contribution of constant disks. I'm not sure if that makes sense. So you're saying
I'm saying that p times that the local system within the open closed would be p times the cross alpha.
yes.
Doesn't say that this particular submanifold is not realized. I mean, okay, so p times the cross is realized.
Okay, give me 1 second. Let me try to understand. Maybe we talk about this afterwards. Okay, thank you. But thanks for the suggestion. Yeah, but in any case, I think there are still some questions that I don't know concerning this. Okay, so I think I'll end my talk here.